Could you build a structure that stays standing for 4,000 years without ever writing down the word gravity? Ancient civilizations did exactly that, repeatedly on every continent. Structures still standing today, aqueducts that carried water downhill across hundreds of miles, using nothing but a precisely calculated slope, temples aligned so precisely to the movement of the sun and stars that modern engineers still study how they pulled it off. None of that happens by accident. It happens when you understand a force well enough to build your entire civilization around obeying it. Here's the thing nobody tells you about ancient physics. Understanding a force and naming it mathematically are two completely different achievements, and history tends to reward only the second one. So let's actually work through what ancient humans knew, piece by piece, because the real story is far more impressive than "they had no idea." Start with the single, oldest, most universal piece of evidence, the plumb line. It's absurdly simple. A weight, called a plumb bob, tied to a length of string, allowed to hang freely. And yet that simple tool depends entirely on one very specific, very consistent fact about the universe, that a hanging mass will always settle into pointing toward the exact same direction, straight down toward the center of the Earth. Egyptian builders used plumb lines to align the Great Pyramid of Giza, and modern surveys have found its base is level to within just a few centimeters across a footprint of over 5 hectares, and its sides align to true north with an accuracy of a few hundredths of a degree. That's not the achievement of a culture guessing blindly. That's the achievement of a culture that had identified a completely reliable, repeatable natural behavior and built an entire engineering discipline directly on top of it, thousands of years before anyone wrote down a formal theory of what was actually causing that behavior. Now here's where it gets interesting, because the plumb line wasn't an isolated trick. It was a foundational piece of a much larger, working relationship with what we'd now call gravitational behavior. Roman engineers, building the aqueduct system that supplied water to cities across the empire, faced an extraordinarily precise problem. Water only flows downhill, and the slope required is remarkably small, often just a matter of a few centimeters of vertical drop for every 100 meters of horizontal distance, over stretches that sometimes ran more than 50 miles. Too steep, and the water moves fast enough to erode and destroy the channel. Too shallow, and it simply stops moving, or worse, flows backward. Roman surveyors solved this using a tool called the chorobats, a long level wooden instrument with a water-filled groove that let them measure minute changes in elevation. The Pont du Gard aqueduct in southern France, still standing after roughly 2,000 years, drops just over 17 meters in elevation across its entire 50-kilometer length. That's an average gradient of roughly 1 in 3,000, a level of precision that would be genuinely difficult to achieve with modern laser levels, let alone anything Rome had access to. You cannot successfully engineer water flow across 50 miles of terrain without a deep, functional, tested understanding of exactly how mass behaves when nothing is holding it up. Here's the thing, nobody tells you about how far back this kind of practical understanding actually goes. It isn't just engineering, it's astronomy, and the evidence there is even older. Ancient Babylonian astronomers, working from meticulous nightly records kept for centuries, successfully tracked the movements of the 5 visible planets and documented recurring patterns precise enough to predict lunar eclipses. Clay tablets recovered from Babylon, some dating back well over 2,500 years, record something called the Saros cycle, a repeating roughly 18-year pattern in the alignment of the sun, earth, and moon that reliably predicts when eclipses will occur. Predicting an eclipse isn't a lucky guess. It requires recognizing that celestial bodies move in genuinely consistent, mathematically describable patterns, governed by something, even if you don't have a name or a formula for what that something is. You can't build a reliable predictive model of the heavens by assuming the universe behaves randomly. The entire practice only works if you've correctly identified that there's an underlying, dependable rule at play. That's the wild part. Long before anyone described gravity as a force acting between masses, ancient astronomers had already effectively treated celestial motion as governed by consistent, learnable rules, and built increasingly accurate predictive systems around that assumption. Now, here's where it gets genuinely fascinating, because some ancient thinkers didn't stop at practical observation. They tried to explain why. The Greek philosopher Aristotle, writing in the 4th century BCE, proposed one of the first formal theoretical frameworks for why objects fall, arguing that everything in the universe has a natural tendency to move toward its proper place, with heavy elements like earth and water naturally moving downward toward the center of the cosmos, and light elements like air and fire naturally moving upward. It's wrong by modern standards in several fundamental ways, most notably in his claim that heavier objects fall faster than lighter ones. But here's the thing nobody tells you about why that theory still matters. It represents something genuinely significant. A deliberate, systematic attempt to explain falling motion as a universal, physical principle, rather than something mysterious, magical, or arbitrary. Aristotle's physics dominated Western scientific thought for close to 2,000 years, not because nobody ever questioned it, but because it offered a coherent, internally logical framework that made testable predictions, even flawed ones. Centuries before that, in 7th century India, astronomer and mathematician Brahmagupta wrote something in his text, the Brahmas Futa that reads strikingly close to a genuine theory of gravitation. He described the Earth as having an inherent attractive quality that draws objects toward it, explicitly comparing it to how water naturally flows downward, and framed falling motion as the result of this attractive property rather than objects simply seeking their natural place, the way Aristotle had argued. Brahmagupta wasn't working with modern mathematical tools, and his description lacked the precision of a testable equation, but the core conceptual leap that Earth itself actively pulls objects toward it, rather than objects simply moving toward where they belong, is a meaningfully different and more accurate idea than what dominated Greek and later medieval European thought for centuries afterward. Roughly 300 years later, in the Islamic Golden Age, physicist Ibn al-Haytham and later scholars including al-Biruni pushed considerably further. Al-Biruni, working in the 11th century, calculated the radius of the Earth with remarkable accuracy using trigonometric observations from a single mountaintop, and explicitly reasoned about the relationship between an object's weight, its distance from the Earth's center, and how forcefully it would be pulled toward the ground. Persian polymath Abu Rayhan al-Biruni and physicist al-Kazini, writing in the 12th century in a text called The Book of the Balance of Wisdom, described gravity as a force directed toward the center of the Earth, explicitly noted that this force should logically decrease with distance from that center, and used precision-balanced scales to measure the specific gravity, essentially the density, of dozens of different substances. That's not folklore. That's a testable, quantitative theory of gravitational attraction, developed roughly 500 years before Isaac Newton was even born. Here's the thing nobody tells you about Newton's actual contribution because it gets consistently oversimplified into a single moment involving an apple. Newton didn't discover that objects fall. Every human being who ever lived already knew that. What Newton actually did, formalized in his 1687 work Philosophia Naturalis Principia Mathematica, was demonstrate mathematically that the same force pulling an apple to the ground and the force keeping the moon in orbit around the Earth were one and the same universal phenomena, expressible in a single precise equation relating mass, distance, and gravitational attraction. That's an extraordinary achievement, genuinely one of the most important unifications in the history of science. But it was a mathematical formalization and unification of a force whose practical effects, and in some cases whose theoretical existence, thinkers across multiple entirely separate civilizations had already been working with, measuring, and even explicitly describing for well over 1,000 years before he was born. So if humans understood gravity's effects this thoroughly for millennia, why did it take until Newton for anyone to actually nail down the math? Now here's where it gets interesting again, because the missing piece wasn't observation. It was mathematics itself, specifically the mathematical tools required to describe continuously changing motion. Newton needed to describe how an object's velocity changes at every single instant as it falls or orbits, a problem that requires calculus, a mathematical framework Newton himself had to invent, alongside Gottfried Leibniz working independently around the same time, specifically to solve this exact category of problem. Ancient and medieval scholars had extraordinarily precise observational data, and often correct qualitative reasoning about how gravity behaved. What they consistently lacked was a mathematical language capable of expressing continuous change with enough precision to generate testable, universal predictions covering everything from a dropped stone to a planetary orbit within a single unified framework. The physics in a real sense was already partially understood. The mathematics needed to fully formalize it simply hadn't been invented yet. Put all of this together, and the honest picture of ancient humans and gravity looks almost nothing like they had no idea. Egyptian builders using plumb lines to align monuments still standing, and still precisely level 4,500 years later. Roman engineers calculating gradients so fine that modern surveyors still study how they achieved that accuracy without modern instruments. Babylonian astronomers predicting eclipses centuries in advance by treating celestial motion as governed by consistent, learnable rules. Aristotle building an entire, if ultimately flawed, physical theory around why things fall. Brahmagupta, in 7th century India, describing Earth as actively pulling objects toward it rather than objects simply seeking their place. Islamic Golden Age scholars like al-Biruni and al-Kazini explicitly describing gravity as a force directed toward Earth's center, correctly reasoning that it weakens with distance centuries before Newton formalized the same basic relationship mathematically. None of these traditions were working in isolation with full knowledge of each other's conclusions either. Babylonian astronomical records influenced Greek astronomy. Greek philosophy was translated, studied, and rigorously debated across the Islamic world for centuries, where scholars extended and corrected it using new mathematical and observational tools. Indian astronomical and mathematical work, including Brahmagupta's, traveled along trade routes into the Islamic world and eventually into Europe. Newton, working in 17th century England, inherited the accumulated output of every one of these traditions, whether he credited them explicitly or not, and had access to a body of recorded observation, mathematical technique, and theoretical debate that had been building continuously across multiple continents for well over 2,000 years before he ever picked up a pen. None of that fits comfortably into the story where gravity simply didn't exist, intellectually speaking, until an apple allegedly fell on the right person's head in the 17th century. The real story is closer to a genuinely global, multi-thousand-year relay race. Different civilizations, working independently and sequentially across Egypt, Rome, Babylon, Greece, and the Islamic world, each pushing the practical and theoretical understanding of gravity a little further forward, refining the tools, sharpening the math, testing the predictions against reality, generation after generation, until the pieces finally existed for one person to tie them all together into a single, unified law. So picture that ancient builder again, standing at the base of a half-finished pyramid, plumb line hanging perfectly still in their hand, checking a wall's alignment against a force they had no formal name for and no equation to describe. They didn't need the math to trust the result. They'd already tested it, thousands of times, against a universe that never once broke its own rule. That structure is still standing today, 4,500 years later, level and true, built entirely on an understanding of gravity that history rarely bothers to give them proper credit for.